Okay, everybody, let's go ahead and get started with the empirical risk minimization lecture. And when I say empirical risk minimization, what I want you to think about is like average loss minimization, and specifically how to minimize the average loss over an entire data set. So we'll go ahead and begin by recapping mean squared error, and then we'll talk about how to minimize the mean squared error, and then we'll get into what absolute error is and how to minimize the mean absolute error. And we'll compare contrast mean squared error and mean absolute error when you might want to use one over the other. And then we'll go ahead and look at a practice exam problem, or we'll look at it and post an explanation of how to solve it on the class forums or class Q&A website. So let's start by kind of recapping what mean squared error is. So if we think back to the example that we've been working with, and that's commuting time versus home departure time. So what time do we leave and how long does it take us to get to work? So when we leave from home, for example, if we leave at a little past 7, might take us 100 minutes to get there. In this case, we have a data point. If we left a little after 6, it would take us about 85 minutes to get to work. And so we wanted to figure out kind of like how do we build a model to capture this real life data generating process. And to start with, we thought that to introduce this idea of the hypothesis function, h of x. And right now there's two possible models for the hypothesis function that we've sort of begin to talk about. First one being the constant model, h of x equals h, and the other one being a simple linear regression model. And so for example, actually, I'll use colors for this. So for the constant model, we say that we might predict just a single value, perhaps 70 in this case. And so regardless of whatever our departure time is, we're going to guess 70 is how long it'll take us to get to work. So whether we leave at 11 or at 8 or at 6 a.m., we're going to just say 70. And we're going to think that 70 is perhaps the best time we could predict. And so we'll kind of talk a little bit about how do we determine which of the minutes is the best minute to choose for the constant model. And then thinking about a regression model, that wouldn't just be a straight line. That would be some sort of best fitting line, which would probably look a little bit something like that. And that would give us a range of values for minutes depending on departure time that we would predict. And that model is certainly much more complex than the constant model. So we'll get into that in a little bit. But first, we're going to take a look at the constant model and how to find the best h for that model based on the data set that we have. So if we think back to mean squared error, in this case, we have some sort of data set. So we have 72, 90, 61, 85, 92, and we want to find the mean squared error for this data set. Then we're going to plug each of these values in here, and we're going to take those values and we're going to subtract something from them. So what we're doing is we're taking, in this case, an actual value minus a predicted value and squaring it. So 92 is an actual value from our data set, and then we're going to subtract some value, square it, and then we're going to multiply it by the total number of data that we have in our data set, total number of values that we have. So in this case, it'd be 5 because we have 5 pieces of data. And that's going to give us the mean squared error for the constant prediction h. And why is it the constant prediction? It's a constant prediction because we're going to plug 100 in for each of the h's, because as we said in the previous slide, our constant model is one that just goes horizontal. We don't really vary it. So if we plug in 100 for each of our predictions and we subtract that from the actual value in the data set, square it, multiply it by 1/5, we come up with this value 538.8, which is the mean squared error of this data set. And we know that the smaller of an error we get, the better it is. So the question here is 100 gives us 538, but is there a better value that we can plug into this function right here, r squared, that will give us the minimum error? And what we're going to learn by minimizing mean squared error is that that's going to give us the best value to plug in here, the best h. So what does that actually kind of look like? So we can represent mean squared error as this convex function, and it's essentially just a parabola. And we're going to try and find the value that gives us the vertex right here. So this is what we're going to call h star. And that's h star because it's the h that minimizes this function, mean squared error. In the previous example, we had 100. 100 isn't the best value. 100 might be somewhere here or here. Doesn't really matter. But, well, I suppose we could look at it. If it gave us 538.8, 500, so it would be somewhere probably around here. Regardless, there's a number of h's that we could put into this equation, but there's only one best h, and that's h star. And so by minimizing mean squared error, we find what h star is. And that's what we're going to look at. So far, we've looked at mean squared error as this sort of function right here. And this is mean squared error in its general form. It's general because we have y sub I and we have n, and this is just saying that for any number of elements in a data set, we're going to subtract the actual value from the predicted value and square it. In this case, we've written this equation in terms of h, so y, because h is the only unknown that we have. N and yi are known. N is just the number of data points in our data set, and y is going to be any number, any value in our data set that's a actual value. So we know what all the y's are. We just have to go look them up. And we're going to iterate through each of these y's when we do this. If we expand the summation, then we're going to iterate n times and get n times y values, and we'll plug those into our data set. So for example, this one we had 5 is our n, and we have all of our y's here. So with this general form of mean squared error, we want to take this equation and then try and find what the best h is, which will minimize mean squared error. So how do we do that? What is the system that we'll use to find this h star? And we could kind of brute force this in a way and try and find random values of h all around this data set, all around this function, and try and find the minimum one that way. But that's tedious and ultimately is not something that we can really do. But we can find h star using calculus and all the fancy stuff that you've learned during the 20 A, B, and C series. So what we'll talk about next is how do we actually take the mean squared error and how do we minimize it using these tools. Let's go ahead and start by minimizing mean squared error. And the first thing we'll do is take the derivative with respect to h, and we'll set that equal to 0, and then we'll solve for h star, which will be the best h, which minimizes mean squared error. And then we can perform a second derivative to make sure that we found a minimum. So what does this actually look like? Well, you think back from calculus, if we have a function and that function is the sum of two other functions, so in this case, if we have a function c and it's the sum of function a and b, then the derivative of c is just the derivative of function a and the derivative of function b. And typically, I believe people, what's the saying? The derivative of a sum is equal to the sum of its derivatives. So it's essentially what's happening here. We have this yi minus h squared, and we have a yi minus h squared for every single y in our data set, which we have n number of y's. And so we just need to take the derivative of yi minus h and take it many times. And then we're going to add them up and multiply by 1 over n, and that will minimize mean squared error for us. So let's put on our calculus hats. and go ahead and do that. So we need to use a combination of the chain and power rule here, and we'll go ahead and bring the 2 down. So we have 2 yi minus h multiplied by the derivative of yi minus h with respect to h, and that's just going to further reduce into 2 yi minus h times -1, y -1, because remember that yi in this case is just a constant. It's in our data set, and we're looking it up. Yi minus h is the general form in this case, but that's just a constant. So we just take it with respect to h, which in this case will be -1. And that just gives us -2 yi minus h. You could also say this is -2 times, or 2 times h minus yi, but -2 times yi minus h is a little bit of a better way to say it, because it follows more in line with the process that we're doing. We're taking the actual values, our yi's, and subtracting the predicted values from them to get our loss. So this is, in essence, the operation that we're going to take to determine the minimum for mean squared error. Okay, so at this point, take a look at this, pause the video, and I'll rewrite the steps there, the result that we had from the last slide up here. So d h squared, and that gave us -2 yi minus h. So pause the video, try and answer this question. We'll go ahead and pause it, and I'll be back in a few seconds, and we'll continue going. Okay, so what is the correct answer here? E is going to be the correct answer. Why E? Well, if you think back to calculus, the key idea here is we want to deal with this 1 over n. What does that mean? So if we have some function, c of x, that equals something times another function, a of x, and here k is some constant, like, you know, our 1 over n, then we can simply pull it out, and we can write so we essentially just pulled this constant out into the front of the derivative. So if we do that for here, we have 1 over n multiplied. So we take this -2, multiply it out, which gives us our -2 over n, and then the sum, which is for all of our data points, y minus h. Okay, let's go ahead and start our 4-step process for solving or minimizing the loss from mean squared error. The first thing we're going to do is, well, we want to do something with this 1 over n, and want to kind of kick that out. And then we also want to take the derivative and distribute that within the summation. So we can begin by, let's start with the derivative and add that in. So we have 1 over n. So we have 1 over n summation derivative. Okay, and we've already done the y minus h squared, the derivative of that. So this will give us 1 over n And we can take the -2 and multiply that out. And that's going to just go ahead and give us -2 over n yi minus h. Okay. So first step of minimizing this is done. We've got the derivative for r squared of h. And we can go ahead and take this now, and we're going to want to set it equal to 0 in order to figure out what the h star is. So let's go ahead and do that. So with the derivative of r squared of h, and we'll just take this guy and bring it over. So that will be -2 over n h, and we'll set that equal to 0. Okay, so what's the first step here? Well, we want to deal with this constant, so we can just multiply that to both sides. Specifically, we can multiply -2 over n and -2 over n, and that'll be nice because we'll be able to cancel all this stuff, and of course 0 times -2 over n just gives us 0. So this is going to give us, where should I write this? Yeah, let's go over here. This is going to give us the sum of I equals 1 over n equals 0. Okay, so we can go ahead and rewrite this as 1 yi minus of h, so they're equal to 0. Luckily for us, we have this h here, and we can go ahead and simplify this greatly. This we really can't simplify anymore. It's just the summation of the y sub I. So we can go ahead and let's go for blue. Deal with this sum of constants, and we know that if we have let's go ahead and put this over here. We have the sum of h. Well, that's really just going to equal the number of h's we have. So we're going to have h plus h plus h, and we're going to have that this whole thing well, n times. So this can just be easily rewritten as n times h. So we can go ahead and further simplify this as n I and h equals 0, and we can go ahead and okay, so what do we have here? Well, the further we simplify this, we'll wind up getting our h star. So what we can say is if we set h star is equal to the sum of n, I equals 1 yi over n, this winds up giving us essentially just the mean. So this right here is the mean of all of our y's. So our answer becomes okay, so this right here is our answer. And this is our H star. So H star in this case is just the mean of the data set. And we can verify that this is a minimizer and not a maximizer for mean squared error. That's H star acts as a minimizer by taking the second derivative. Let's go ahead and do that right now. So if we have, yeah, we'll start over here. Actually, start over here. We have r squared of h okay, so in order to find if this is a minimizer or a maximizer, we've got to take the second derivative of this. So let's go ahead and do the second derivative with respect to h. So it's dh of r squared of h, which is going to equal, and what it will equal is essentially, where is it? Kind of this thing right here. So that's negative 2 over n times n I equals 1 I minus h squared. Well, actually it would be squared in this case. We've already taken that out since we have it right here. Okay, so need to take the second derivative of that. So that's going to look like so r squared of h so negative 1 y. Again, we're dealing with yi, which is just going to be a constant. So it goes away. So all we have is the negative h to deal with, which will give us negative 1. And we can further simplify this to negative 2. And of course, those will cancel out. Which will give us 2 is greater than 0, so a positive 2 from this right here. And positive 2 means that the function, I suppose, r squared of h in this case opens upwards, so it's a minimizer and not a maximizer. And this step right here, so how we got from here to here is it's sort of like what we did over here, where if we have so all we're going to have is essentially a bunch of a little better. Negative 1 plus negative 1. Negative n. Okay, so we verified that this is a minimizer and not a maximizer. So we got a positive 2 So what does this really mean? Let's kind of maybe take a step back and think about this idea, mean squared error, and what's really going on here. We found for our data set and for trying to take r squared of h and minimize mean squared error, we found that the h star, which is the minimum value, just winds up being the mean. Or if you think back to stats, y bar. And so the fact that this winds up being the mean, like the h star is the mean, has everything to do with two things. One is that we're trying to predict what h star is going to be for our constant model. That's really important. This may not actually be the mean, like h star may not be the mean if we were doing something other than the constant model. It just happens to be the fact that we're doing the constant model. And we also have the squared loss function. If we were doing something like the absolute loss function, like mean absolute error, then it may not be the mean. It's not guaranteed. So it just happened to work out this way because of these two options. And if we think about it, it makes a lot of sense, because if we have a constant, like let's think about it in terms of sort of what would make the most sense to us without any math at all. If we've got a set of values from a data set and we want to find the value that would minimize that data set as far as like a prediction goes, then the mean makes a lot of sense if we're thinking about it. So it'd be sort of like, what would be a good example? Let's say that, I want to try and determine the average grade for, a class. Then I would just look at the grades that people have already gotten and just pick the average. And so if I get new students for the same class next quarter, I would just predict that the average from the students who took the class the previous quarter would be the grade that the students this quarter are going to get. That makes a lot of intuitive sense. However, there's a lot of problems with that. The problems that we'll uncover, we'll see in future slides, specifically when we compare it to the mean absolute error. But if we just think about it real quick, it makes a lot of sense, because we're, again, dealing with just the constant model. All we're saying is we only have one value, and we're always going to predict that value. And so no matter what data we see, if we can only choose one value to predict, then the mean makes a lot of sense. And we've just shown mathematically that it does make the most sense. H star has been shown mathematically to be the mean, and it makes a lot of sense if we have the constant model as the model we chose, and we're taking the squared loss function. Those are the two things we have to keep in mind. Another way of thinking about it, or writing it, is that we're just taking, in this case, h star is the argument of the mean squared error. So what we've essentially done is solve an optimization problem. We've optimized h star, some input to a function which minimizes this being the mean squared error. So this is just an optimization problem. And in reality, machine learning is all about solving optimization problems. I know this is a theoretical foundations of data science class, but a lot of the theoretical underpinnings of machine learning have a lot of great transferability to many problems in data science, even if you're not using machine learning. So this is, especially when we're dealing with things like optimization, mean squared error. These are really fundamental and good ideas to think about and learn about. So let's tie this back into our modeling recipe. Remember that we have three things. We want to choose a model. In this case, we chose the constant model. So that just being h of x, our hypothesis function, which takes in x and gives us back, and we get an h from it, which is our prediction. So no matter what x we put in, we get h. Again, thinking about the example of new students in a class, those new students, no matter what parameters those students might have, their previous grades, their major, their high school GPA, doesn't matter. When I get a new student, an X, I'm making a constant prediction, H. So that's the model we chose. And then we have a loss function. In this case, we chose the loss function of mean squared error. So and then we've had to find some way to minimize that loss to find the optimal model parameters. So in this case, what's our H star? What is that value that's going to minimize mean squared error? In this case, that winds up being just the mean. But this is all changeable. We might have some other model, like a regression model, which our hypothesis function in that case would be, something that looks like this, completely different than just h, right? This is a lot more complex than just h. Our loss function could be different. Instead of, squaring y minus h, we might do something that looks like, which we're going to cover next, but it could be something that looks like that. And we might have other model parameters, beyond just h star. So there's a lot of that goes into the modeling recipe, and what we've shown here is pretty much some of the simple stuff that we could do, but it's a good foundation for thinking about these more complex models and more complex loss functions. So we'll go ahead and, if you have any questions, take a moment to pause and think about what we've done, look through some of the slides. And obviously this is not a real live class. So if you have questions, put them onto our class forum or class Q&A website, and we'll go ahead and try and answer them as quickly as possible. So let's take a quick little break, and then we'll start with the next section. Okay. So we've seen mean squared error. Let's look at another loss function. So we started by trying to compute the error from some value that we have, some variable in our data set, and then what that prediction was and how far that prediction was from the variable would be our error. And of course, in this case, our hypothesis function of hx is, of course, just h. But in general, we have some value, and we're going to subtract our prediction from it. And we looked at the squared loss because we wanted to get rid of negative numbers. So we had some way of actually summing up the total loss. Another thing we could do is use absolute values to sum up essentially the total loss as well. So we want to kind of compare these two loss functions and see how they both work. So in this case, we have this line here, which is 80. And we have our 80 is the mean for our loss. We calculated it as, given this data set here, the mean squared error, or I guess the value that minimizes the average squared loss, is 80. So I'll keep it like this. So for squared loss, 80, which is the mean of our data set of y's. It minimizes. Okay, so we want to kind of compare this to absolute values. So let's use green. So if we take 72 and we plug it into absolute loss, we take our y of I, and we put that in to here, and we subtract 80 from it. That's going to give us 8. Same thing if we take 90 and we subtract 80 from it. Absolute value of that will give us 10. 61 will be 19, 85, 5, and 92 will be 12. And that's going to be our absolute loss. If we take our squared loss, we use 72, that's going to be 8. We're going to square it. So 64, 10, square it, it's 100, 19, 361, 5, 25, and 12, 1, 44. And this is going to be our squared loss. So, I mean, already absolute loss looks better, because if we sum up all these, it's less. But what does that really mean? So let's try and compare these two things together. What we kind of want to see is if we have, let's put this at 80 right here. So this was 80, and we want to see kind of how far away are all these things. And if we just kind of take the information right here and we map it onto this kind of, I guess you could call it like a number line, we're going to get, and this is, what color did I use? Green for absolute and purple for squared. Purple for squared and green for absolute. So let's start with green. So if we went to 72, we were 8 away, and this is to 61 was 19 away, and went to 85, 90, and 92. So that was 5, 10, and 12. 5, 10, and 12. Okay. So that's sort of how the data is spread from what was H star for squared loss. And if we look at squared loss, we have 72, 61, 85, 90, and 92. And this was 64 and 100 for 61, 70, for 61, 72, 361, and 64. So 361 and 64. And 64. And the other 3, 144, 25, and 100. So 25, 100, and 144. So the question here is, we know that 80 was our H star for squared loss. We don't know what H star is for absolute loss yet, but we know that this value of 80 is the one that minimizes the sum distances of all of these 5 data points from 80. So is this the best one for absolute loss? Well, we don't know. Sometimes they are the same. In this case, though, they're not the same. In fact, we can just do some back of the envelope testing and see if we move 80 to either 79 or 81. So let's just assume we bump it up 1 to 81. This is for the absolute. Then that's essentially going to subtract 1 from 19 and 1 from 8, and we'll add 1 to 5. Well, if you take the negatives into account, we're going to wind up actually reducing it by just a little bit. So 81 winds up becoming a better H star for absolute loss than 80. So we know that 80 is not the best for absolute loss. We can do better, which means, like we did before, we have to minimize absolute loss to truly find the H star. So what does that look like? Well, essentially it's pretty much the same thing, except now, instead of having yi minus h squared, we have the absolute value of yi minus h. And we're going to go ahead and do the same process. So let's go ahead and try and minimize for mean absolute error now. Again, this is the same 4-step process to try and solve for h star. We're going to try and take the as best we can, and there's some caveats, and we'll see why. But the derivative of absolute value y minus h. And specifically, remember, we're finding the derivative of the individual loss for this specific y minus this specific h. Of course, in this case, we're using the constant model, so the h's are the same. But this is going to apply for all of the absolute values for all the individual derivatives when we sum them up, just like what happened with the squared loss. So what does this look like? Well, it really helps to sometimes draw a picture, but here we have a plot of yi minus h, and what this is a piecewise linear function, and the reason why is because there are 3 cases for what happens when we're looking at this plot. In this case, there are times when h is going to be larger and less than whatever your yi is. And we want to be able to look at this and take the derivative of it, but we're going to have to handle these 3 cases separately. So essentially, what we have, maybe I'll use purple. We have the case where h is less than yi, so that's going to be h less than yi. And then we're going to have the case where, we'll switch it for blue, h is greater than yi. And then we also have the case when h, and I'll use h is equal to yi, and that's down here at the corner. And essentially this is going to be just 0 because the absolute value of yi minus h is equal to the absolute value of 0, which is just equal to 0. And then, of course, so that's this case. And then for the case where h is greater than yi, that's just h minus yi. And then, of course, we have the case where you have y minus h. So, and we'll further put these in. Like that. Like that. And these are really the 2 cases that we really care about. We'll handle the 0 stuff a little bit differently. So taking the derivative of this is quite a bit different than taking it before when we had squared, because we had a parabola then, and now we have this kind of weird v thing. So what does this actually look like when we take the derivative? Well, we have three cases, and maybe we'll put that, yeah, let's put that here. So the derivative with respect to h of yi minus h, the absolute value, is going to give us three cases. And those three cases are where we have, and let me see what colors I used before. So for h is less than yi, we use purple, so we'll start with there. So for the case where we have h is less than yi, that's going to be over here. What's the slope? And the slope of this is just 1. So 1. Wait a second. Less than y, no, that's incorrect. So say h is less than y, it was purple. So that should be on the other side, because that's yi minus h. So that's going to be actually over here. So this is going to be the case where h is less than yi, so yi minus h, and this slope will be -1. So -1 for h, which is less than yi, and then the case for h is greater than yi, we used blue, so h is greater than yi, and this would be h minus yi, and this is going to be a slope of 1. Okay. So what happens down here at the corner? Well, this is going to be undefined. I think I used yellow there. For yi is equal to h. Why is it undefined? Because we have a slope which goes down, and slope. So we have slope of 1. Let me rewrite that actually. So this point right here, the slope that approaches this point from both directions is different. And because of that, we can't define what the slope is at this particular point. So it's going to be undefined. We're not going to necessarily deal with this when y does equal h. So for instance, if h was 80 and we had a data point that was 80, we're not going to care about it at this point. But that's why we kind of have the derivative in quotes here, sort of the derivative, 2/3 of the derivative. But we'll skip that for now, and we'll just figure out what do we do for minimization when the points that we get for yi are along these areas. Okay, so we've kind of found the derivative of y minus h. Let's go ahead and find the derivative of the absolute value with respect to h for the mean absolute error. So what does this look like? Well, and maybe we can rewrite these over here to kind of help us. Remember, we had this idea of it being -1 when h was less than yi, and then +1 when h was greater than yi. We're ignoring the case where y is equal to h, and this is the derivative of yi. Let's write that down as well. For the absolute value of yi minus h. Okay, so that's what we're going to use because that gives us this part right here. So thinking about when we did this with the mean squared error, we were able to pull out that 1 over n constant and then redistribute the derivative within the sum. Because remember, derivative of a sum is equal to the sum of its derivatives. So what does that look like? That's going to give us 1 over n, so we pull that out. And now we have the derivative of the absolute value of yi minus h. And essentially all this really is just a sum of a bunch of ones and zeros. Remember, because the derivative of the y minus h is just either 1 or -1. So this sum is just a bunch of ones or -1s. And specifically, it's a sum of ones when it's this case, h is greater than yi, and it's a sum of -1s when h is less than yi. So we can make that a little more explicit. The two cases are +1 or -1 when h is greater than yi or h is less than yi. So we can actually use these two cases here and here, and we can write this out a little bit. Let's go for, yeah, I think that's fine. Okay, so we have 1 over n, and we have the number of cases where h is greater than yi. So where h is greater than yi minus the number of cases where h is less than yi. And specifically, it's minus h is less than y, minus the number of cases where h is less than yi, because we're going to sum all those up and take the number and multiply it by the n. So what does this actually look like? Well, we can draw a little picture. So if we go back to, what was it? Right here, we had 80 for the mean, and we were looking at the absolute value. We said what happens if we were to increase it to 81. Well, let's see what happens. Come on. Okay, so if we take these 5 data sets, or 5 points in our data set, which was 61, 72, 85, 90, and 92, I believe. So it'd be 61, 72, 85, 90, and 92. Hopefully those are the same ones. If they're wrong, then just those are the 5 that we used before. And in this case, let's say we had, let's use red. We're going to have h is equal to 81, that's what we said. So that's going to fall somewhere around here. And we take the derivative of r, technically r absolute, of 81. That's going to give us number of cases on the number of cases of h is greater than y minus I minus number of cases where h is less than yi. So that gives us 2 minus 3 over the number, which is 5. So -1/5. Now, what is this -1/5? This -1/5 is essentially the slope of mean absolute error. So for this specific example, in general, though, whatever this value that we're calculating is, whatever this equals is our, make that a little better, is our slope of mean absolute error, MAE. And this is the slope of mean absolute error is a pretty important concept to keep in mind. This will come up a lot. So now that we have the derivative of mean absolute error with respect to h, we go to step 2 and 3, which is to set it to 0 and figure out what that H star actually is. Remember, in this case, we said that H was 81. It's not H star, it's just H is 81 as an example to show how we would calculate the slope of mean absolute error. But in order to figure out what H star actually is, we have to minimize it by setting it to 0, like we did before. So let's go ahead and do that next. So in this case, we have the derivative for absolute error with respect to H is 1 over n. We said of H is greater than yi minus the number of cases where H is less than yi. So we'll shorten this to number with H is greater than yi minus the number where H is less than yi. We'll go ahead and rewrite this part a little bit better. And we're going to go ahead and set that equal to 0. So first obvious thing we can do is we can get rid of this constant by multiplying it by n. So we times this side by n, this side by n, which cancels that out. This n times 0 is just 0. So we get rid of that constant, and now we have the number of, we'll make it explicit, number of H minus or less greater than yi minus the number of H less than yi. Of course, we can just, that equals 0, we can just add this to that side. So we'll add this to this side. That just gives us the number of H is greater than yi, which is going to be equal to the number of H is less than yi. Now, what does this look like? Think about it. We have all of our data. Okay, so we can, let's pick a different color. We have all of our data, and we can put all of that data onto a line and say these are our yi's, kind of like we had over here, because 61, 72, 85, 90, 92 were our yi's. The H star, the value on this number line, is the one that sets the number of y's greater than and less than H being equal. So in this case, it's going to be somewhere around here. And really, this is the median. That's all this this really is. So if we have a data set with 5 numbers, actually, that would be right here. It's just H star winds up being the location where the number of data points are equal on both sides of it, which is what this is saying, and that winds up being our median. So the points to the left of H is equal to the points to the right of H. So that is which is just the median. Okay, so we've discovered that the median actually minimizes the mean absolute error. So that's to say that H star is the median. This is pretty interesting. One good thing we can do is we can take a look at the graph of the function for the absolute error with the data points plotted and get a sense for what this actually looks like. So if we look at our sample 5 data set, 72, 90, 61, 85, and 92, which we've been using for the last several slides, we'll see that there's this graph here which has a bunch of bends in it. And we have bends here, 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 and another small one right there. And these are the actual areas on the graph where our data points are. So for example, we have 61, and 61's right here. Then we have 72, and we have 85, and 90, and then 92. So what is this actually telling us? Now I want you to think about what happens to the slope of the mean absolute error as it goes through these data points, and then ultimately also what happens at these data points. And remember, specifically, this right here too, we're undefined at these kind of hinge points, these corners. So let's try and find, what's happening for the, let's try and calculate the slope when we try and select an H. So let's pretend that the H is at 89. So somewhere around here. Now I can do it a little better. So at 89, that's where we want to put our H at. So in this case, remember we have derivative of absolute value with respect of H equals 1 over n. And this is the number of left minus the number of right. And so that's basically, we're going to do 89 and one-fifth. So remember we have 1 over n, we've got 5 data points. So 1/5 over, and now let's see. We have 89, and we have 3 to the left and 2 to the right. We also know that at this point, we should be positive for the slope. So we're gonna have a number at the left, that's gonna be 3 minus 2. So that's gonna give us 1. And that's gonna give us 1/5. 1/5 is a positive number. So 1/5 is the slope right there at 89. This also works for if we had, something 91 would be 4 minus 1 multiplied by 1/5 gives us 3/5 positive. And if we were on the left side and we went to negative numbers, we'd have a negative slope. So this works out quite well. Now, this is the case when our data set has 5 values. So we know that H star is going to be, well, I guess a better way to put it is that we know that there's going to be a number on the left and a number on the right, and we can pick one value. But if we have an even number of data, then something different happens to the plot. We no longer have a unique H star. Like in the case where there's an odd number, we can have a unique H star. But in this case, there's not a unique H star. In fact, and here we have 61, and we have 72, and 75, 72, 75. We have 85, 90, and 92, 85, 90, and 92. So this is, draw that a little better, 90 and 92. Okay, so what happens? And particularly what we're really interested in looking at is this part of the chart right here, or the graph, where there's this flat section where there's no slope. So when we have an even number of data points, there is no unique H star. In fact, H star can take on any value, infinite number of values even. between 75 and 85. So we could write this as, we'll use green, 75 and 85. So 75, that'd be less than or equal to whatever our H star is going to be, which should be less than or equal to 85. Okay, so all of these points within here, all these H stars minimize mean absolute error. So they all work. That's an interesting thing to point out. So what's kind of the big picture here? We have this idea of the mean absolute error, and we can plug in any H and we can find out what that mean absolute error is. But the H star, the one that minimizes it, winds up being the median. And we see these interesting properties where the best constant prediction is always the median. And when there's an odd number in our data set, we have a unique answer, right? Because there's always going to be a middle number. And in the case where there's an even number, we don't have a middle number, but we have a continuous range between the two middle numbers that can take on H star. So any point within those two. And that's pretty much the same for the mean squared error, right? We had the same process that we took, but the value for H star differed between both of them. In one case, we had one number. In this case, with median, we have two cases where there's a unique H star and then a range of H stars. So let's bring it back to this idea of the modeling recipe. So this time we chose a model. It was the same exact model. We have our constant model, so our hypothesis function, which equals H, one value of H, regardless of what the Y is. And we chose to look at the mean absolute error function. So that would be the absolute function of yi for H, which is the absolute of yi minus H. We also looked before at the mean squared error. So this is the equal yi minus H squared. So these are the two loss functions that we looked at. And we saw that for each of these loss functions, the mean absolute error, the mean squared error, that the H star that we calculated were wildly different. In the case of the mean absolute error, H star wound up being the median of the data set. And for the squared error, it wound up being the mean. Clean this up a little bit. Okay, so the fact that we wind up getting the median and the mean has a lot to do, not so much with these two loss functions. These two loss functions are very common. What's not common here is the constant model. That's a very uncommon thing to choose. Perhaps as a baseline, it's an interesting model, and it can certainly be used when looking at histograms. But the fact that we had the constant model made the average loss function for median and mean work out very nicely for the absolute and the squared loss. Now, which of these is better? On the surface level, we saw that we got much lower numbers with the mean absolute error compared to the mean squared error. That's not something that we can really say for certain makes the mean absolute error much better than the mean squared error. In this case, that's how it worked. And perhaps if we took in something like the root mean squared error, we could further evaluate it. But what we'll talk about in the next lecture is how do we go about comparing loss functions. In particular, we'll look at comparing the absolute to the squared loss function, and we'll see how that sort of works. The whole point here is this idea of empirical risk minimization. And as I said in the beginning of this lecture, when you think of empirical risk, think about average loss. And what we've done with both of these is we've taken the average loss, either the absolute or the squared, across the entire data set, and we've calculated what that loss is. And this is essentially one of the the foundational building block to machine learning is you have to have some way to quantify loss. Because if you can't quantify loss, you can't really have a good way of taking a machine learning model or an algorithm and improving it with data. So this idea of average loss is very important for that. Yeah. Perhaps this is a good general idea to keep in mind is that really we could have picked any loss function, and in reality there are a lot of loss functions: hinge loss, Hoover loss, mean squared loss, absolute loss, root mean squared error. There's lots of losses that you can use, but the process generally is the same with these loss functions. So think about any questions that you might have and post them online to our class forum or question and answer site, and we'll get back to them and answer them as soon as possible. For next lecture, we're going to talk about the comparison of these loss functions, and we'll recap on how we calculate the mean and median again briefly. But think about these things and go back through the slides and make sure you understand the math behind them. It was not too bad with these simple derivatives, but make sure you understand that. And this lecture's gone pretty long, so for the practice exam problem, well, before we go into that, homework one should have been released, or will be released soon, depending on when you watch this. And we'll ask you to take some of the concepts that we've talked about in the lecture and to show or prove some of the various properties or features of things like mean squared error and mean absolute error. So for a quick practice, and we'll have a solution to this answer. But take a look at this. Define the extreme mean of a data set to be the average of its largest and smallest values. So it's like the mid-range. So for the function f of x equals negative 3x plus 4. So we have some sort of function, and we're going to scale and shift it essentially. And we want to find the extreme mean for that function for the data set that's ordered. So we've got an ordered data set, and we're going to find the mid-range. So go ahead and take a look at that, try it out, and this is a good example of some of the homework and exam questions that we'll be asking you. And we'll go ahead and see you for next lecture.